Hello ladies and gentlemen, this is Properties and Interactions of Waves and correlates with chapter 14.2 and 14.3 in your textbook. Your key concepts for this video are: what are the amplitude, wavelength, frequency, and speed of a wave? How are wavelength, frequency, and speed related? What are the ways a wave changes direction? And what are the two ways waves interact? So let's first talk about wave parts. Remember from the last video that the top of a transverse wave is called the crest, shown by these red X's, and the bottom of the transverse wave is called the trough, shown by these blue X's. We're going to add two more words to your vocabulary: wavelength and amplitude. Wavelength is exactly what it sounds like. It's the length of the wave. You measure this by measuring the distance between any corresponding parts of a wave. It's easiest to go crest to crest or trough to trough, but you can do it from any point in the wave. Just make sure that you're going all the way to that same point on the wave, not just halfway, which is why it's easier crest to crest or trough to trough. Now, amplitude is measuring the distance from the rest or the midline to the highest point, the crest, or the lowest point, the trough of a wave. It will be the same no matter if you measure up or down, as long as you're going to the furthest most point. Now, on a longitudinal wave, this looks a bit different, but is still quite similar. Wavelength is still between two corresponding parts, so easiest between two compression points or two rarefaction points. Now, amplitude, just based off this drawing, is really hard to measure because we don't know how far the particles are vibrating side to side, but the maximum distance from their rest point to where they vibrate would be their amplitude. On to wave properties. The first thing you need to know about is the frequency. This is the number of wavelengths that pass a certain point in a certain time. We generally use about 1 second as our time interval. Frequency is measured in a unit called Hertz, which we abbreviate Hz. If, as in our example here, 14 wavelengths pass a certain point in 1 second, we would have a frequency of 14 Hertz, because 14 wavelengths over 1 second gives us 14 Hertz. In contrast, if only 4 wavelengths pass the point in 1 second, we have a frequency of 4 Hertz. When you listen to the radio and you change the station, you've actually changed what frequency of radio waves that your stereo is picking up, which is what allows you to hear different radio stations. A second property of waves is the speed. Just like we've already learned, the SI unit is meters per second, and different waves have different speeds. A wave's speed will stay the same as long as the medium, its temperature, and the pressure are all kept the same. But if one of those things changes, the wave's speed can also change. Now, you've probably heard that light travels faster than sound, and it's true. Light waves travel at 299,792 kilometers per second. To put that in perspective, that's fast enough to go around the Earth 7.5 times in 1 second. Sound, on the other hand, is much slower, which is why in a lightning storm or a thunderstorm, you can tell how far away it is based off the number of seconds between seeing the lightning and hearing the thunder. They both actually happen at the same time, but sound takes longer to get to you the further away it is, so you hear it later. Speaking of light, you might have heard of light years. Scientists use light years as a measure of distance, not time, to see how far things are in our universe. They calculate it by seeing how long light travels in a year. A few years ago, scientists were able to detect light from a galaxy 13.4 billion, with a B, light years away. That's really far if something as fast as light has taken 13.4 billion years to get here. Now that you know some of the properties of waves, let's talk about how they're related. You know, to calculate speed of a wave, you can do distance over time. But often with waves, you don't know the distance or the time, but you know its wavelength and you know its frequency. So what we do is we use those two. Wavelength we represent with the symbol lambda, and frequency we represent with a fancy F. And to calculate speed, you would do speed equals wavelength times frequency. And yes, like many of our calculations this year, there is a handy conversion triangle to help you isolate specific variables. Wavelength and frequency go on bottom, and speed is on the top. Now to discuss how waves change direction. There are three ways they do this. The first is through reflection. This is when a wave hits a surface and all or part of it can't go through, so it bounces back. This is how mirrors and echoes work. There's a really cool effect that reflections cause called a standing wave. For those of you that play instruments or sing, when you make different notes, you're making standing waves. The waves in your instrument are reflecting back, so they appear to be standing still. The parts where they overlap, those are called nodes. And the parts at the maximum amplitude, those are called antinodes. The longer the wave being reflected, the lower the sound. So think about on guitar, if your fingers are way up on the first fret, it's a low sound. Or on a flute or a clarinet, if all the holes are compressed down, it's a really low note. The second way waves change direction is through refraction. If you've ever noticed how a straw seems broken, or fractured, in a cup of liquid, or observed a prism make a rainbow, you've seen refraction. When a wave enters a new medium at an angle more or less than 90 degrees, it causes one side of the wave to slow down more than the other side of the wave, so it bends. Different mediums will bend the light and other waves in different amounts. The third way waves bend and change direction is through diffraction. No matter where you're sitting in class, if I'm standing in the hall and I say something, you can all hear me because the waves come through the doorway and then diffract around and spread out throughout the entire room. Alternatively, if you're hiding behind something, sound still reaches you because it bends around the barrier and reaches your ears. Beyond changing direction, waves can also interfere or interact with each other. There are two types of interferences. When two waves traveling in opposite directions meet, if their crests line up, the amplitude of both their crests add together to create a combined bigger wave before continuing on their way with their original amplitude. This is called constructive interference because they're building each other up. The opposite of this is destructive interference. This is when the waves combine and the combined wave's amplitude is less than the amplitude of each individual's wavelength. This happens when one crest lines up with the trough of another wave. This can simply minimize the amplitude or, in some cases, completely cancel each other out if the waves' amplitudes are equal. That's it! Be sure your notes have all the key concepts and vocabulary, and feel free to try this challenge question.